Hi there, thanks for joining the third in the gravity series, the third video. Okay, so in the previous video we calculated all the forces, we had a job that calculated all the forces that apply. So each object is applying forces on other objects. In this video we're going to follow the job that its heroic mission is to take the forces that were calculated before in the previous job and to turn them into acceleration, velocity, and position. And then later on we'll taking those positions and updating the scene. Okay, so this is relatively simple how we convert force into acceleration. Given the formula force equals mass times acceleration, we want to turn this around so we have acceleration expressed in terms of force and mass. So acceleration equals force divided by mass. Acceleration and force are vectors, but mass is just a number. Okay, so once we have acceleration for the object, we can then figure out the change in velocity by multiplying the acceleration by the delta time. So that will give us the change in velocity. So the new velocity equals the old velocity plus the change in velocity. And then we can do the same thing with position. So once we've figured out the new velocity, we can multiply that by delta time. That gives us the change in position. We can add that to the old position to get the new position. And that is really all this job needs to do. We're computing the position, and then later on that can be used to update the transform. So what do we have? Our gravity, acceleration, velocity, and position job. Well, it's saying what it's about. It's a long name, I know. Okay, so it's an I job, again, not an I parallel 4 job, or I job parallel 4. Reason for that is, like before, we're going to be reading and writing into the same structures. It is possible to rearrange this a bit to make it an I job parallel 4 if we really want to, but that would require more arrays, like an input array and an output array, and it's more complication than we need. And we get plenty of performance out of this anyway, so why bother? Not only that, why allocate all that extra memory? You know, why complicate the system and everything that we're doing? So optimization, the key trick of optimization is balancing complexity with performance. You know, it's getting the right trade-off between the two. So what do we have? Okay, so we have our forces array, which in this case is read-only. We have our another array of our components. Now in this case, for instance, where we'll be calculating the delta position, and so we have to read from this bodies array, take the current position, calculate the delta, and add that on, which is why we're reading and writing onto this particular array. And so it is not read or write only, it is unmarked, has no attribute, therefore it is both read and write. And we have delta time, so that will be like time.delta time. That'll be passed in through the begin method. So we have again, like in the previous job, this job has its own begin method. It's a static function, effectively. It will take the job handle to the previous job. Now I've called it dependency because I always call it dependency because it's a dependency. The job handle here is from the forces job. And obviously we're going to take our newly calculated forces array and the bodies, and we're basically going to, you know, construct the job structure, and from there we're going to schedule it. That's really what happens here. Like I've said before, by having begin in the same struct that is the job itself, all of the job related code is in one place, including how it's scheduled. That's the benefit. Our execute method is going to loop through them all and basically update each component, which is the gravity component. Right, so it's going to update that gravity component. That's all that has to worry about. The update component, as you can see, is basically asking to calculate the acceleration based on the forces. This will be a new acceleration based on the forces just previously calculated. It won't take into account any previous accelerations. It's not read and write, this is just plain write. But once we have that acceleration, we can actually figure out the velocity. Remember, velocity it's a vector, so it is direction and magnitude. And acceleration is also a vector. And so that's where we do take the current velocity and we compute a new velocity based on the acceleration. So you can see that, we're taking the forces, from that we calculate a acceleration. From the acceleration we calculate a change in velocity. From velocity we calculate a change in position. This could have been done over multiple jobs, but it's probably going to be wasteful. So my idea was, let's try it this way. If it's fast enough, this will be how it is. If it needs somehow to be spread out across a number of threads, and if that made it faster, then that's what we'd do. This turned out to be fast enough, so we did this. Okay, and how's the calculations done, right? So here we have compute acceleration, another expression method body, basically taking the forces. So remember that there's that physics formula, force equals mass times acceleration. Well, that means that acceleration equals force divided by mass. And that's what we're doing here. We're taking the force, or the sum of, which is the sum of all the forces for a given object, and we are dividing it by the mass for that same object. And we're hoping to hell that none of those masses are zero. That would be a sticky problem. That would cause an exception. Divide by zero, exception. Not good. We have here the compute velocity change. So the change in velocity is really just the acceleration times the delta time, right? The change in time since you last computed anything. So that works out very nicely to be delta time, which is constructed from time.delta time. If we want to know that, we look up here and we see that the begin function is indeed using time.delta time. So that works out perfectly. Okay. So we have our delta time, and then times the acceleration rather, to get our change in velocity. And then from that, the change in position happens to be just the change in position, mind you. So we take the velocity and we multiply that by delta time. Pretty simple, really. And so then once now remember, this is taking a body in and then it's making some changes and returning the body. Because it's a struct, it's a value object. So you've got a value on the stack, which is a copy out of the array into the stack, passed into this method. We make some changes in the stack, which is nice and fast, and then we return the resulting structure again on the stack. And that's what happens up here, where it gets invoked. So that's why we are replacing the whole structure, the whole value object. And actually, that's how it needs to be done. If we try to do a dot, say position equals something or other, that tends not to work. So this is exactly how it needs to be, as it turns out. Now, as you can see, it's pretty simple. That's really all there is to it. So at the end of this job, the array of gravity components now has, acceleration and velocity, which we don't really need later on. We just need the position, but it will have an updated position. And that will feed into yet another job. So there we are. That's all there is here. Right, so let's look at the other job. So, the translation job. This job's job is to take the new positions and basically shove that back into the game objects, transform. And so we can see here that we have an array of bodies again. Happens to be the same array, but this time it will be read-only. Again, we have our begin function to create the job and to schedule it. So here this will be given the array of bodies and a transform access array. Now, again, this transform access array has to be constructed pretty much at the start of the program and basically just persisted for the life of the program. And then, of course, we're going to return a new job handle. And this takes the job handle, sorry. It takes the job handle that was returned from the previous job, which is the acceleration, velocity, and position job. This one is using an iJob parallel for transform. So this one will in fact issue across multiple threads, worker threads. So this will actually, this will complete in a shorter time frame. And here we are explicitly using the iJob parallel for transform extensions static class and calling its schedule method, passing it the job and the transforms and the dependency. So the transforms is passed in as part of the schedule. This is a special kind of schedule, a special kind of job. Okay, and then in the execute method, guess what? It's really, really simple. We take the position float 3 out of the bodies array and we assign it into the position vector 3 on the transform. Now notice this. Unity's float 3 in mathematics has a nice way of casting automatically a float 3 into a vector 3. And that works pretty nicely. That's everything. Rather short job. Dare I say, it gets the job done. Sorry, had to do it. So there we are with the third video in the series complete. We've looked at our last two jobs in the overall pipeline, being our acceleration, velocity, position job, that super long name one, and the job that updates the transform for all the game objects in the scene. So the next trick, actually, in the next video, we'll look at what I call the gravity system class and how that's implementing a system very similar to, say, an ECS system, right? So remember that the intent, the design with this was to make a mini ECS. So we'll look at that and we'll compare this and say, okay, how does this fit the ECS architecture conceptually? Right, not in comparison to Unity's ECS, which is a different animal. This is just ECS as a philosophy. If you like this video, please absolutely press that like button. Please let your friends know who are also into game development, who are using Unity and who are trying to eke that last little bit of performance out of their game loop, or shift all that effort out of the game loop and into a job. So share away, subscribe if you haven't, that'd be fantastic. It'd be super good if we can get lots of likes on this video. I think at this moment I haven't seen 100 likes yet on any video. So if you could do 100 likes, that'd be fantastic. That'd be exceptional, out of this world. Okay, thank you, and we'll see you in the next one about the system.